Hello and welcome to Midnight Space. Before we drift into the quiet mysteries of the cosmos tonight, go ahead and like this video and subscribe so you can join us on countless celestial journeys, and I'm curious, where are you watching or listening from tonight? Maybe you're gazing at the moon from your backyard, or perhaps you're cozy in a room letting your imagination soar across the night sky. Wherever you are, the moon above us shares a story with every corner of our world, a story that has fascinated humans for millennia. Tonight, we're going to explore a question that's both simple and profoundly mysterious. Why does the moon always show us the same face? That familiar, serene face in the night sky. It never blinks, never turns away. To casual stargazers, it seems almost alive, always watching. But what is the science behind this quiet cosmic choreography? How did the moon's slow spin and orbital dance lock it in such a perfect, unchanging gaze toward our planet? Over the next chapters, we'll uncover the subtle forces, the invisible tugs of gravity, and the patient hand of time that shaped this eternal alignment. We'll meet the scientists, both celebrated and quietly brilliant, whose theories and discoveries help explain this cosmic mystery. And we'll peek into the high-level, mind-expanding perspectives on how this celestial phenomenon connects Earth, life, and the universe itself. So settle in, take a slow breath, and let your mind float among the moon's silent hills and craters. Tonight, we're not just looking at the moon, we're understanding the story it tells, a story written in the language of gravity, time, and the gentle rhythm of the universe. Hello there. Have you ever noticed that whenever you look up at the moon, that familiar face seems to be gazing back at you, unchanging, serene, and timeless? It is the same face that people have admired for millennia, the same face that inspired myths, poetry, and quiet contemplation. But behind this apparent stillness lies a subtle and fascinating dance of physics, a story written in gravity, rotation, and time. The question is simple but profound. Why does the moon always show the same face to the Earth? When we glance at the moon, the first things we see are its striking features. There are the deep, dark plains known as the Luna Maria, broad basaltic plains that formed billions of years ago when molten rock seeped to the surface from massive volcanic activity. There are the highlands, pale and rugged, forming the moon's mountainous regions that rise sharply above the Maria, often riddled with countless craters. These craters, from the smallest pit to the enormous gaping basins, are the scars of countless impacts over the eons, remnants of collisions with asteroids and comets that have peppered the moon since its earliest days. Each of these features is a marker in time, a physical record of the moon's ancient history, and yet all of them remain on the same side that faces our planet. The scientific explanation for this apparent immobility is a concept known as tidal locking. In simple terms, tidal locking occurs when an astronomical body's rotational period, the time it takes to spin once around its axis, matches its orbital period, the time it takes to circle its partner. For the moon, this period is approximately 27.3 days. This synchronous rotation ensures that the same hemisphere of the moon constantly faces the Earth. It is as if the moon, after billions of years, has come to a quiet agreement with our planet, aligning itself perfectly to maintain a consistent gaze. To appreciate this more deeply, it helps to think of the moon not just as a passive observer in the night sky, but as a laboratory of celestial mechanics. Its relationship with the Earth provides a living example of gravitational dynamics at work. The Earth's gravity stretches the moon slightly, raising what are known as tidal bulges. These bulges generate friction within the moon's interior, dissipating energy over vast periods and gradually slowing its rotation until it matched its orbit. This is not a dramatic or sudden process. It is a patient, almost imperceptible negotiation of forces occurring over billions of years, revealing the remarkable patience of the universe. The moon's surface features, from the expansive mare imbrium to the cratered expanse of the far side, all reflect this tidal relationship. Even though the far side of the moon remained hidden from human eyes until the Luna 3 mission in 1960, its discovery only reinforced the understanding that the moon is tidally locked. Every crater and volcanic plain we see tells a story of both the moon's violent past and its gentle gravitational tether to Earth. As we look at the moon, we can also appreciate its subtle complexity. Tidal locking is not simply a curious coincidence, but a natural outcome of the laws of physics. Isaac Newton's law of universal gravitation lays the foundation, describing how every mass in the universe attracts every other mass, with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. This gravitational attraction between the Earth and Moon, while invisible, is profoundly consequential, shaping the Moon's spin, orbit, and orientation. It is a force that is constant and yet patient, sculpting the Moon's motion with a quiet, inexorable persistence. The Moon also serves as a reference point for understanding similar phenomena elsewhere in the cosmos. Many moons in the solar system, from Jupiter's Io to Saturn's Enceladus, are tidally locked to their planets, exhibiting the same alignment between rotation and orbit. By studying the Moon, we gain insights not only into our immediate celestial companion, but also into the universal mechanics that govern moons and planets across the universe. Scientists and research groups at institutions such as NASA and the European Space Agency have devoted decades to measuring and modelling these effects, using tools like lunar laser ranging to detect minute changes in distance and orientation with extraordinary precision. These measurements confirm that the Moon continues its slow, consistent journey, maintaining its steadfast orientation toward Earth. While the Moon may appear unmoving, it is in fact engaged in a subtle ballet. Its rotation is synchronized, yes, but there are slight oscillations, gentle librations, that allow us to glimpse slightly more than half of its surface over time. These minute movements, hardly noticeable without precise observation, remind us that even in seeming stillness there is motion, and that motion is governed by profound principles that connect matter, energy, and time. Tonight, as you allow your mind to wander over the craters, plains, and highlands of the Moon, consider the delicate balance that holds it in place. Think of the forces at work, the slow grinding of tidal friction, and the quiet shaping of gravity over eons. This is a story not of sudden explosions or dramatic upheaval, but of patience, alignment, and cosmic harmony. The Moon's familiar face is not a static tableau. It is a testament to the subtle artistry of the universe, a living example of physics, history, and time converging in a silent celestial gaze. And so, as we begin this journey, let us settle into the quiet grandeur of the Moon. Let your imagination drift across its cratered landscapes, across the Maria and highlands, and into the unseen forces that maintain its eternal, gentle watch over our planet. In exploring why the Moon always shows the same face, we are not merely learning a fact about a celestial body. We are witnessing the patient, persistent hand of the universe, guiding our companion in a timeless gravitational embrace. Long before the advent of telescopes, humans were already captivated by the Moon's ever-present glow and the steadfast face it turned toward the Earth. Ancient observers noted its changing phases, the waxing and waning of its light, and the familiar patterns of dark plains and bright highlands. Across the globe, the Moon became a marker of time, a guide for planting, harvesting, and navigating the changing seasons. In the Fertile Crescent, early agricultural communities used the Moon to regulate calendars, while in East Asia, scholars meticulously recorded lunar cycles to predict eclipses and seasonal changes with remarkable accuracy. The Moon's constancy and appearance inspired myths and legends as well. In Chinese folklore, the Moon is inhabited by the Jade Rabbit, eternally pounding the elixir of life, a figure whose presence mirrors the Moon's unwavering gaze. The Mayans too wove stories around the Moon's phases, linking it to deities of fertility, rain, and agriculture, and tracking its cycles with astonishing precision in their elaborate calendrical systems. As human curiosity matured, the Moon became a subject not only of myth but of meticulous observation. In the 17th century, astronomers with modest telescopes began to chart its surface with increasing detail. Galileo Galilei, famously peering through a small refracting telescope in 1910, revealed that the Moon was not a perfect smooth sphere as previously thought, but a world marked with mountains, craters, and valleys, suggesting a history of impacts and geological activity. Beyond Galileo, other careful observers contributed to the growing map of the Moon. Johannes Hevelius, a Polish astronomer in the 17th century, created some of the earliest detailed lunar atlases, naming regions and features that are still recognized today. Giovanni Riccioli, an Italian Jesuit in the same period, introduced a naming system for lunar craters that persists, honoring philosophers and scientists from Aristotle to Tycho Brahe. embedding human curiosity into the lunar landscape. Different cultures approached lunar observation with unique perspectives and purposes. In East Asia, astronomers of the Song and Ming dynasties recorded lunar eclipses, comets, and the timing of the moon's appearance against the background of stars, creating records that remain invaluable to modern science. Their meticulous attention to detail allowed later astronomers to refine models of the moon's orbit, rotation, and even slight deviations in its motion, known as librations. Meanwhile, the Mayans developed sophisticated mathematical models to predict eclipses and phase cycles, blending astronomy with ritual and agricultural planning. These early records demonstrate that even without modern instruments, humans could recognize patterns, track motion, and begin to question why the moon always presented the same familiar face, hinting at an understanding of regularity and rotation long before the underlying physics was known. These observations laid the groundwork for scientific inquiry. By noting that certain features never shifted out of view, early observers began to suspect a relationship between the moon's spin and its orbit around the Earth. While mythology provided stories to explain the moon's constancy, careful record-keeping revealed empirical regularities. Astronomers could chart the moon's movement night after night, year after year, and see that its rotation must be synchronized in some way with its orbit, even if the mechanism remained a mystery. This early recognition of synchronous motion, although not understood in terms of gravitational theory at the time, was a crucial step toward the development of concepts such as tidal locking and angular momentum exchange, ideas that would be formalized centuries later through the work of George Howard Darwin and other pioneers of celestial mechanics. The moon also inspired practical and philosophical reflection. Sailors in the Mediterranean and Indian Oceans observed the moon to aid navigation, noting the predictable positions of its features relative to the horizon and the stars. Philosophers in Europe speculated on its nature, oscillating between ideas of a perfect celestial sphere and a world scarred by violent forces. This tension between idealized perfection and empirical observation mirrors the journey of science itself, moving from speculation towards systematic measurement, from story to model. Over time, as instruments improved and records became more precise, it became evident that the moon's rotation was not arbitrary. Its persistent orientation toward Earth suggested a relationship governed by invisible forces, waiting for scientists equipped with Newtonian physics and later gravitational theory to explain. In reflecting on this historical journey, we see that the moon's familiar face is not just a passive observation, it is a story of human curiosity, cultural interpretation, and careful measurement. Each crater noted by Hevelius, each phase tracked by Mayan astronomers, each eclipse recorded in the archives of the Song dynasty, contributed to a growing recognition of the moon's regularity. It is a regularity that invites deeper questions. What forces keep the moon in this consistent orientation? How did it arrive at this state over billions of years? And what does this reveal about the nature of motion, gravity, and the interconnectedness of celestial bodies? By tracing these historical perspectives, we can appreciate that our understanding of the moon's steady gaze emerges from both careful observation and a profound human desire to understand the rhythms of the cosmos. Even the myths, whimsical though they may be, echo truths that modern science later confirmed. The jade rabbit pounding immortality, the Mayan moon deities regulating agricultural cycles, these narratives reflect a keen awareness of the moon's cycles and constancy. They remind us that humans, across time and cultures, have recognized the moon's steadfast presence and have sought to make sense of its silent patterns. By observing the moon with both imagination and rigor, our ancestors laid the foundation for centuries of discovery, culminating in the precise measurement and modeling that would eventually explain tidal locking, gravitational torque, and the subtle, patient forces that govern the moon's enduring face. In appreciating this history, we also gain a sense of the moon as a bridge between myth and science, between imagination and empirical observation, and between the night sky of the past and the carefully charted celestial mechanics of today. The moon's motion is a delicate balance of rotation and revolution, a celestial choreography that has captured human imagination for centuries. When we speak of its rotation, we refer to the moon spinning around its own axis, completing a full turn roughly once every 27.3 days. Its orbit, the path it traces around the Earth, takes the same amount of time to complete. This remarkable synchronization is known as synchronous rotation, a state in which the Moon's rotational period matches its orbital period so precisely that the same hemisphere is always oriented toward Earth. It is this alignment that gives us the familiar view of the Moon's face, while its far side remained hidden from human eyes until the Luna 3 spacecraft transmitted the first images in 1960. Synchronous rotation is not a trivial occurrence. Achieving this precise balance required the patient action of gravitational forces over billions of years. Early astronomers were aware of the Moon's predictable motion, but lacked a complete understanding of the mechanisms behind it. Among the lesser-known contributors to our understanding was Simon Newcomb, a 19th-century American astronomer and mathematician who meticulously measured the positions of the Moon and planets. Newcomb developed refined lunar tables that corrected earlier observational discrepancies, allowing for greater precision in calculating the Moon's rotation and orbit. His work revealed the subtle irregularities in the Moon's motion and laid the groundwork for understanding the complex relationship between rotation and revolution. The Moon's orbit is not a perfect circle, but rather an ellipse with a modest eccentricity of approximately 0.05. This means that the distance between the Earth and Moon varies slightly over the course of its orbit, ranging from about 360,000 kilometers at its closest approach, known as perigee, to roughly 405,000 kilometers at its farthest, or apogee. This elliptical shape causes small variations in orbital speed, a phenomenon that contributes to what astronomers call longitudinal libration, the slight rocking of the Moon that allows observers to see a little beyond its mean edge. In addition, the Moon's axis is tilted by about 6.7 degrees relative to its orbital plane, a modest inclination that produces latitudinal libration, giving Earthbound observers occasional glimpses over its northern and southern edges. Studying the Moon's rotation and orbit historically presented significant challenges. Before the development of precise telescopes and later, photographic and radar measurements, astronomers had to rely on visual observations, carefully charting the positions of craters and prominent surface features night after night. Atmospheric distortion, imperfect instruments, and human error all contributed to the difficulty of measuring subtle motions. Even small deviations, such as the few arc-seconds caused by libration, were hard to detect without consistent long-term observation. Nevertheless, through patient recording and collaboration, astronomers were able to confirm that the Moon's rotation was indeed locked to its orbit, revealing a remarkable and previously unappreciated regularity in celestial mechanics. The Moon's rotation and orbit also illustrate fundamental principles of physics. The precise synchronization of spin and revolution is the outcome of the interplay between gravitational forces and angular momentum. As the Moon's early spin gradually slowed due to interactions with Earth's gravity, it reached a stable equilibrium in which further slowing was minimal. This state of synchronous rotation is maintained by tidal forces, a mechanism that will be explored more deeply later, but at its core involves the stretching and flexing of the Moon's material in response to Earth's gravitational pull. Over long periods, energy is dissipated as heat within the Moon's interior, gradually bringing the rotation into alignment with the orbital period. It is also worth noting that the Moon is not alone in exhibiting synchronous rotation. Many natural satellites in the solar system, from Jupiter's Europa to Saturn's Enceladus, display similar behavior, suggesting that tidal locking is a common outcome in celestial systems, where a smaller body orbits a much larger one. These comparisons allow astronomers to test theories of orbital evolution and energy dissipation across a range of planetary environments. By examining the Moon, we gain a local, tangible example of these processes, a laboratory close enough for detailed study and precise measurement. Observational studies continue to refine our understanding of the Moon's motion. Modern methods, such as lunar laser ranging experiments conducted by NASA beginning in 1969, involve bouncing laser beams off retroreflectors placed on the Moon's surface by Apollo astronauts. These experiments measure the Moon's distance with millimeter precision and confirm the stability of its synchronous rotation. Minute variations, including small accelerations in orbital motion and tiny oscillations in orientation, provide insights into the internal structure and the history of energy transfer within the Earth-Moon system. They also demonstrate the extraordinary patience required for the Moon to reach its present state, a testament to the quiet, persistent influence of gravitational forces over cosmic timescales. In contemplating the Moon's rotation and orbit, it is fascinating to consider how such seemingly subtle mechanisms have profound consequences. its synchronous rotation not only determines which hemisphere faces Earth, but also influences tides, stabilizes Earth's axial tilt, and shapes the environment in which life evolved. The Moon's motion is a silent yet powerful force, governing rhythms that have affected cultures, agriculture, and navigation for thousands of years. The alignment of rotation and revolution, once hidden from human understanding, reveals the elegance of celestial mechanics and the intricate connections between bodies in the solar system. As the Moon traces its path across the sky, completing a full orbit in harmony with its slow, measured rotation, we can appreciate the delicate balance of forces that sustains this configuration. Every crater, every mare, every shadowed ridge is held in place not by accident, but by the patient shaping of gravitational interaction and angular momentum. The Moon's steady face is the visible manifestation of these invisible forces, a reminder that even in the apparent stillness of the night sky, there is motion, energy, and history at work. This synchronization sets the stage for understanding tidal interactions, the gradual slowing of rotation, and the extraordinary precision with which the universe orchestrates its dance of planets, moons, and stars. The Moon's serene presence in the night sky is maintained by forces that are invisible, yet immensely powerful. Among these, tidal forces play a central role, shaping the Moon's rotation, its orbit, and even the subtle bulges that ripple across its surface. The concept of tidal forces, first explored rigorously by George Howard Darwin in the late 19th century, describes how the gravitational attraction between two bodies produces stretching along the line connecting them. In the case of the Earth and Moon, the Moon's gravity pulls on Earth's oceans, raising tidal bulges, while Earth's own gravity stretches the Moon ever so slightly. These forces are not sudden or dramatic. They operate over immense spans of time, slowly redistributing energy and angular momentum across both bodies. Darwin proposed that these tidal interactions gradually dissipate rotational energy, producing measurable changes in the Moon's spin. He suggested that the early Moon, once spinning more rapidly, experienced friction caused by its own tidal bulges, which generated internal heat and gradually slowed its rotation. Over millions and then billions of years, this continuous energy transfer brought the Moon's rotation into synchronous alignment with its orbit, producing the state we observe today. The elegance of this theory lies in its combination of gravitational physics and energy conservation, demonstrating how simple principles can explain a complex and stable celestial arrangement. Gravitational torque is another crucial component in this story. Torque, a measure of the twisting force that acts on an object, occurs whenever gravitational attraction interacts with an uneven mass distribution. On the Moon, this means that the slight elongation caused by Earth's pull experiences a torque that resists misalignment with the Earth-Moon axis. This resistance slows any rotational speed that deviates from the orbital period. The result is a self-correcting system. If the Moon were to rotate slightly faster or slower than the orbit, the torque would act to bring it back into precise synchronous rotation. Modern celestial mechanics, drawing on Newtonian physics and refined through centuries of observation, confirms that this mechanism is remarkably stable, maintaining the Moon's steady face with a precision that endures across eons. The long-term dissipation of energy through tidal forces is subtle, but powerful. Each tidal bulge, each minuscule flexing of the Moon's material, converts rotational energy into heat, which is then radiated into space, or distributed internally. This gradual process, measured over billions of years, demonstrates that even gentle forces given sufficient time can produce profound outcomes. Researchers such as Harold Jeffreys in the early 20th century expanded on these ideas, considering the influence of the Moon's internal rigidity and elasticity on the rate of rotational slowing. Jeffreys showed that the Moon's partial rigidity means that while tidal forces act constantly, the internal structure absorbs and dissipates energy in a manner that allows synchronization to occur without catastrophic deformation, preserving the Moon's crust and surface features over geological time. Angular momentum conservation is central to understanding the Earth-Moon system. In essence, the total angular momentum of a closed system remains constant unless acted upon by external forces. As tidal friction slows the Moon's rotation, angular momentum is transferred to the Moon's orbit, causing it to move slightly farther from the Earth over time. Measurements confirm that the Moon is receding at an average rate of about 3.8 centimeters per year, This transfer illustrates a subtle dance between spin and orbit, a delicate bookkeeping of energy that has stabilized the Moon's orientation while slowly modifying the distance between our planet and its satellite. The implications of tidal forces extend beyond the Moon's visible face. They influence the rhythms of the Earth itself, from ocean tides to the gradual lengthening of our days. By raising tidal bulges, the Moon exerts a braking effect on Earth's rotation, transferring energy in a reciprocal motion that maintains balance in the Earth-Moon system. This dynamic interplay is a testament to the universality of physics. Gravitational interactions, torque, energy dissipation, and angular momentum are principles that operate across planets, moons, and even exoplanets, shaping their rotational and orbital behavior in predictable yet elegant ways. Observational evidence reinforces these theoretical insights. Precise measurements made possible by lunar laser ranging, in which laser beams are bounced off retroreflectors placed by Apollo astronauts, have confirmed both the Moon's synchronous rotation and its gradual recession. The data show minute variations in orbital speed and orientation, consistent with the predictions of tidal theory. Over centuries, astronomers have tracked the Moon's motion with ever-increasing accuracy, from Simon Newcomb's meticulous 19th century tables to modern measurements at institutions such as NASA and the European Space Agency. These observations provide a living laboratory for understanding the persistent influence of gravitational forces, allowing us to quantify effects that operate on timescales far beyond a human lifetime. Tidal theory also sheds light on the broader behavior of natural satellites throughout the solar system. Many of Jupiter's and Saturn's moons, including Io, Europa, and Enceladus, are tidally locked to their parent planets, often exhibiting internal heating due to continuous flexing caused by gravitational interactions. By comparing these systems to the Earth-Moon pair, scientists can explore how variations in mass, orbital distance, and eccentricity affect the timescale and efficiency of tidal locking. These comparative studies highlight the Moon as a unique yet representative example of gravitational dynamics, providing insight into universal processes while allowing for detailed observation that is impossible for more distant moons. Even the Moon's slight librations, small oscillations that allow us to see slightly more than 59% of its surface over time, can be understood in terms of tidal physics. These movements result from the interplay of the Moon's orbital eccentricity, axial tilt, and the distribution of mass within its interior. Each gentle oscillation is a visible reminder of the ongoing influence of tidal forces, a subtle motion that reflects the underlying balance of torques and energy dissipation. In a way, the Moon is not rigidly fixed. It is flexing, breathing, and adjusting in perfect harmony with the Earth's gravitational pull, maintaining its steadfast orientation while revealing a dynamic and responsive interior. The study of gravitational forces and tidal effects thus provides not only an explanation for why the Moon shows the same face, but also a window into the deeper principles that govern celestial mechanics. From the initial work of George Howard Darwin and Harold Jeffreys to modern observations and laser measurements, the consistent outcome of these forces demonstrates the predictive power of physics over vast timescales. It is a story of gentle persistence, forces that are imperceptible in a human lifetime, acting continuously over billions of years to shape the alignment, rotation, and orbit of a world that has become one of our most familiar companions in the night sky. In contemplating these interactions, one begins to appreciate the elegance of the universe. The Moon's stable face is not a static accident, but a consequence of laws that operate universally, quietly orchestrating motion with precision and grace. The tidal forces that stretch, flex, and torque the Moon are the same principles that govern distant exoplanets, spinning stars, and complex planetary systems. Observing the Moon thus becomes more than a casual pastime. It is an invitation to witness the intricate and patient workings of gravitational physics, to recognize the subtle negotiations of energy and momentum that have unfolded over billions of years, and to marvel at the persistent invisible hands that maintain the cosmic rhythm between Earth and its closest celestial companion. The ebb and flow of the ocean tides are among the most familiar and tangible signs of the Moon's influence on our planet. As the Moon circles the Earth, its gravitational pull attracts the water in the oceans, raising bulges that manifest as high tides along coastlines. On the side of the Earth facing the Moon, water is pulled toward it, forming one high tide, while on the opposite side another high tide occurs due to the inertia of the water resisting the centripetal acceleration toward Earth. This dual bulge pattern is a visible demonstration of the gravitational relationship between our planet and its closest celestial companion, and it is a phenomenon that has fascinated humans for millennia, influencing navigation, fishing practices, and cultural calendars. These tidal bulges are not restricted to Earth alone. The Moon itself experiences subtle stretching caused by the Earth's gravitational pull, producing minuscule tidal bulges across its rocky surface. Although far less obvious than ocean tides, these bulges generate friction within the Moon's interior, dissipating energy over vast spans of time. The study of these effects was advanced by Charles Galton Darwin, son of George Howard Darwin, who applied rigorous mathematical analysis to the concept of tidal friction in the early 20th century. He demonstrated how these small, persistent forces could gradually slow a satellite's rotation, aligning it with its orbital period and producing synchronous rotation. His work built upon the foundations laid by his father and provided a quantitative framework for understanding how tidal interactions shape planetary systems over geological timescales. It is remarkable to consider that the forces producing these tidal effects are incredibly gentle when observed moment to moment. The gravitational attraction of the Moon on the Earth amounts to a small fraction of the overall force acting on the planet, yet over millions and billions of years, the cumulative effect is profound. Ocean tides continuously transfer angular momentum from the Earth's rotation to the Moon's orbit, causing the Moon to slowly recede at an average rate of approximately 3.8 centimeters per year. Simultaneously, the Earth's rotation gradually slows, lengthening the day by a few milliseconds every century. These subtle interactions illustrate the principle that even modest forces applied persistently over immense timescales can produce monumental changes in the motion of celestial bodies. The process of energy transfer through tides also involves the deformation of Earth's oceans and crust, a phenomenon known as tidal dissipation. As the tidal bulges shift with the rotation of the Earth, friction between ocean waters and the seafloor converts kinetic energy into heat, further contributing to the gradual loss of rotational energy. On the Moon, although there are no oceans, tidal dissipation occurs within the solid interior, where microscopic flexing produces heat that slowly alters rotational speed. This continuous, patient redistribution of energy exemplifies how the laws of physics operate consistently across both planetary bodies, revealing a subtle yet powerful mechanism that underlies the apparent stillness of the Moon's familiar face. Observations of tides have not only provided practical knowledge for human activity, but have also informed scientific models of orbital stability. By carefully recording tidal patterns, amplitudes, and timing, early oceanographers and astronomers could infer the strength of the Earth-Moon gravitational interaction. Later, with the development of sophisticated measurement techniques, such as lunar laser ranging, scientists could quantify changes in the Moon's distance and orbital period with unprecedented precision. These measurements confirmed that tidal forces are the key driver of synchronous rotation and play a critical role in maintaining the long-term stability of the Earth-Moon system. Institutions such as NASA and the European Space Agency have collected decades of data supporting these conclusions, providing empirical evidence that complements theoretical models. Cultural interpretations of tides also reflect an understanding, however intuitive, of the Moon's influence. Coastal communities observed that high tides corresponded with the Moon's position in the sky, and rituals, navigation charts, and calendars were often aligned with lunar phases. The regularity of tides provided a sense of temporal order, a natural rhythm that paralleled the Moon's unchanging face. This connection between observation, practical application, and emerging scientific theory illustrates the interplay between human curiosity and the persistent forces of the natural world, bridging folklore and rigorous understanding in a seamless continuum of learning. The cumulative effect of tidal interactions is a demonstration of nature's patience. While a single high tide might seem insignificant, the repeated stretching of oceans and solid bodies over millions of lunar orbits produces a measurable evolution in both rotation and orbit. The Moon's current synchronous rotation is a testament to this slow, persistent shaping. The same gravitational relationship that raises ocean tides also dictates the motion of our satellite, gradually synchronizing its rotation with its orbit and ensuring that the same hemisphere is perpetually visible from Earth. It is an elegant illustration of how interconnected forces, seemingly invisible and subtle, can orchestrate the grand movements of celestial bodies across eons. Even minor irregularities such as variations in coastline shape or ocean depth affect local tides and introduce complexity into the system, yet the overarching gravitational relationship remains consistent. By observing the Moon and the resulting tides on Earth, scientists can study energy transfer, angular momentum exchange, and the dissipation of rotational energy with remarkable precision. The visible ebb and flow of oceans thus serves as a tangible reminder of the immense, patient forces shaping the Earth-Moon relationship. Through careful measurement and observation, tidal dynamics reveal not only the Moon's influence on our planet, but also the universal principles that govern satellites, planets, and the intricate ballet of bodies within the solar system. Ultimately, the tides on Earth and the subtle flexing of the Moon's surface illustrate the power of persistence in nature. Forces that are modest in the short term, applied consistently over billions of years, yield profound and lasting results. The Moon's synchronous rotation, the slow recession from Earth, and the gentle lengthening of our days are all legacies of these tidal interactions. By watching the ocean rise and fall, and by reflecting on the Moon's steady face, we can witness the quiet, elegant mechanisms that govern celestial motion, appreciating the interplay of gravity, friction, and energy that maintains harmony in the Earth-Moon system. The tides, both on Earth and in the Moon itself, are more than a natural rhythm. They are a testament to the slow, persistent shaping of worlds by the invisible hand of physics, sculpting motion and stability with patient, unyielding grace. Tidal locking is a concept that elegantly explains why the Moon presents the same face to Earth, and yet it is a phenomenon that can seem almost magical until we explore the physics behind it. Formally, tidal locking occurs when an astronomical body's rotational period, the time it takes to spin once around its axis, becomes exactly equal to its orbital period around its partner, resulting in the same hemisphere always facing the larger body. In the case of the Moon, this synchronization was achieved through a long and patient interaction of gravitational forces and energy dissipation, a process that took billions of years to bring the Moon into its current state of equilibrium. To understand tidal locking more deeply, it helps to visualize the Moon not as a static orb but as a participant in a cosmic dance. Imagine a dancer spinning while orbiting a partner across a ballroom floor. At first, the dancer may twirl at an independent pace, spinning faster or slower than their path around the room. Over time, subtle adjustments occur. Gravitational pulls between the Moon and Earth act like gentle nudges, slowing or accelerating rotation until the dancer's spin perfectly matches the orbit. This is spin-orbit resonance, a fundamental principle in celestial mechanics that governs how rotational and orbital motions synchronize under the influence of tidal forces. Donald Goldsmith, a 20th century astrophysicist, made important contributions to our understanding of tidal evolution in binary systems, applying the principles of spin-orbit resonance to a variety of celestial bodies. His research demonstrated that tidal locking is not unique to the Moon, but is a common outcome for satellites orbiting larger planets and even for stars in binary systems. Goldsmith showed that as gravitational interactions produce energy dissipation in the smaller body, rotational speed gradually adjusts, aligning with the orbital period. This principle explains why moons such as Europa and Titan are also tidally locked to their parent planets, maintaining a stable orientation that is remarkably predictable. Not all moons achieve perfect tidal locking immediately or at all. Partial locking can occur when the smaller body has an eccentric orbit, or when the tidal forces are insufficient to bring about full synchronization within the age of the system. For instance, some of Saturn's irregular moons display chaotic rotation or temporary spin-orbit resonances, wobbling unpredictably while still influenced by the planet's gravity. Studying these partially locked moons provides insight into the dynamics of tidal evolution and illustrates the range of outcomes that gravitational interactions can produce. It reminds us that tidal locking is not a single endpoint but a process, one that can take multiple pathways depending on mass, distance, and orbital eccentricity. The mechanics of tidal locking can be understood through the exchange of angular momentum and the dissipation of energy. As the Moon's tidal bulges, raised by the Earth's gravity, shift slightly ahead or behind the line connecting the centers of mass due to rotation, a torque is applied that gradually alters its spin. Internal friction within the Moon, caused by flexing and distortion of rock and mantle materials, converts rotational energy into heat, slowing the spin until it precisely matches the orbit. The process is gentle, almost imperceptible on human timescales. Yet over millions of orbits, the cumulative effect is profound, producing a stable synchronous rotation that has persisted for billions of years. To make this concept more tangible, consider a clockwork toy spinning on a rotating platform. If the toy wobbles slightly, friction and interaction with the surface gradually bring it into a rhythm with the platform, until its spin is perfectly synchronized with the motion beneath it. In this way, tidal locking is nature's own form of rhythm correction, a patient alignment guided by forces that are constant, invisible, and remarkably precise. It is an alignment that produces the moon's unchanging face, the familiar view that has inspired humanity for countless generations. Observational evidence confirms these principles. By tracking lunar motion, measuring orbital distance with lunar laser ranging, and modelling the moon's internal response to tidal forces, scientists have been able to reconstruct the gradual evolution of spin and orbit. Institutions such as NASA and the European Space Agency have monitored tiny variations in the moon's orientation, revealing that even minute departures from synchronization are corrected over time through tidal torques. The moon's current synchronous rotation is thus both a product of historical forces and a dynamic equilibrium maintained by ongoing gravitational interaction. The concept of tidal locking also provides insight into broader astrophysical phenomena. Many exoplanets orbiting close to their stars are expected to be tidally locked, presenting one hemisphere permanently to their sun, a state that has profound implications for climate, atmosphere, and potential habitability. Similarly, binary star systems can exhibit synchronized spins, a phenomenon predicted by the same principles first articulated by early tidal theorists. In this sense, the moon serves as a nearby, accessible example of a universal process, a local laboratory where the laws of physics are expressed in a clear, observable way. Even the gentle oscillations of the moon, its librations, can be understood as a nuanced aspect of tidal locking. These small swings result from the moon's orbital eccentricity and axial tilt, allowing observers on Earth to glimpse slightly more than 59% of its surface over time. Libration demonstrates that tidal locking is not an absolute stillness, but a dynamic balance, a careful negotiation between rotation, orbit, and internal structure. It is as if the moon, while perfectly synchronized in its dance, occasionally performs subtle flourishes, reminding us of the living, responsive nature of celestial mechanics. Through tidal locking, the moon teaches us about patience, balance, and the power of cumulative forces. Small, continuous interactions over unimaginable spans of time yield profound stability, producing the familiar, reassuring face we see in the night sky. The concept transforms our perception of the moon from a static companion into an active participant in a gravitational dialogue, a cosmic partner engaged in a carefully choreographed dance with our planet. It is a dance that is slow, elegant, and utterly precise, a testament to the enduring and invisible principles that govern the motions of worlds across the universe. In contemplating tidal locking, we can imagine the moon as a disciplined dancer, perfectly attuned to the rhythm of its partner, never hurried, never faltering, moving through space with patience and grace. Its steady face is a reminder that even in the vastness of the cosmos, patterns emerge, laws persist, and harmony prevails, maintained by the subtle yet relentless hand of physics. The moon we see today, serene and unchanging, was not always so tranquil. In its early history, the moon likely spun far more rapidly, completing rotations in a fraction of the time it takes today. Its surface, still etched with craters and volcanic plains, preserves evidence of a more chaotic and energetic past. Billions of years ago, the moon's rotation would have carried different regions past the Earth in rapid succession, its landscape flashing by like the hands of a clock turning too quickly. Over time, subtle gravitational interactions between the Earth and Moon applied a persistent braking effect, gradually slowing the lunar spin until it became synchronized with its orbit, establishing the steady face we now observe from our planet. The story of the moon's rotational evolution is intimately tied to the question of its origin, a topic that has inspired scientific debate for centuries. George Howard Darwin, son of the famed naturalist Charles Darwin, proposed in the late 19th century a theory known as the fission hypothesis. According to Darwin, the moon was once part of the Earth itself, spun off from a rapidly rotating proto-Earth in its molten infancy. This theory suggested that the Moon would initially have had a significant rotational velocity, consistent with observations of synchronous rotation forming over time through tidal interactions. In contrast, Harold Urey, an influential 20th century chemist and planetary scientist, advocated for the capture hypothesis. He proposed that the Moon formed elsewhere in the solar system and was later captured by Earth's gravity. In this scenario, the Moon's rotation would also have been independent and potentially faster than its eventual orbital period, requiring similar tidal processes to bring it into synchronization. Both theories, while differing in origin, underscore the necessity of gradual energy dissipation and gravitational braking to explain the Moon's current rotational state. Evidence for the Moon's early rotation and subsequent slowing comes from a combination of geological and observational studies, particularly those enabled by the Apollo missions of the late 1960s and early 1970s. Samples of lunar rocks brought back to Earth provide a record of the Moon's thermal and geological history. Radiometric dating of basalts and highland rocks reveals that the Moon underwent significant volcanic activity between 4.3 and 3.8 billion years ago, a time when its rotation would have been faster and more energetically dynamic. Additionally, the distribution and orientation of a large impact basin suggests that early lunar rotation influenced the way meteoroids struck the surface, leaving patterns that are still observable today. By studying these rocks, scientists can infer the internal structure of the Moon and model how tidal forces acted over eons to slow its spin and stabilize its orientation toward Earth. The mechanism driving this gradual rotational deceleration is rooted in the gravitational relationship between Earth and the Moon. As the Moon rotated, tidal bulges raised by Earth's gravity were slightly misaligned with the line connecting the centers of mass, producing a torque that acted against the rotation. This torque converted rotational energy into heat through internal friction within the Moon's crust and mantle. Over millions of years, the cumulative effect of this process reduced the Moon's spin to match its orbital period. It is a striking example of how persistent, gentle forces can produce profound long-term changes. Even small differences in alignment, measured in mere degrees, were sufficient over billions of years to produce the precise synchronous rotation observed today. Modern computational models, informed by these geological and observational data, allow scientists to simulate the Moon's rotational evolution with remarkable precision. By accounting for the Moon's mass distribution, the elasticity of its crust, and the influence of orbital eccentricity, researchers can estimate the timescale over which the Moon achieved tidal locking. These models suggest that full synchronization may have occurred between 4 and 3.5 billion years ago, a period during which the Earth-Moon distance and tidal interactions shaped not only the Moon's rotation, but also its gradual recession from Earth. Observations today, such as those from lunar laser ranging experiments conducted since 1969, provide empirical confirmation of the ongoing interaction, measuring the Moon's drift away from Earth at roughly 3.8 centimeters per year, consistent with theoretical predictions based on historical rotational slowing. Understanding the Moon's rotational history also provides insights into the evolution of other celestial bodies. The principles of tidal braking, energy dissipation, and angular momentum transfer that slowed the Moon's spin are observed in numerous moons and exoplanets, demonstrating the universality of these physical laws. By examining our own Moon in detail, scientists gain a local laboratory for processes that operate across the cosmos, from the synchronized moons of Jupiter to the potentially tidally locked exoplanets orbiting distant stars. The Moon's historical rotation, once rapid and unsteady, thus becomes a model for understanding the delicate interplay between formation, rotation, and long-term gravitational influence. The interplay of theories, observations, and empirical evidence also highlights the scientific process itself. Early hypotheses like those of George Darwin and Harold Urey provide a conceptual framework, guiding observation and experimentation, while Apollo mission findings offer concrete data that refine and challenge those initial ideas. The Moon's rocks, its surface features, and its precise orbital characteristics all converge to tell a coherent story, a tale of a spinning body gradually brought into harmony with its orbit by the patient hand of gravity and the persistent action of tidal forces. Reflecting on this history, we see the Moon not as a passive object in the sky, but as a dynamic participant in a gravitational dialogue with Earth. Its steady face is the outcome of billions of years of interaction, a record of ancient rotations and slow, methodical braking. Each crater, each mare, each highland carries the imprint of this rotational evolution, a physical reminder of the Moon's journey from a fast-spinning companion to the calm, synchronized satellite that has inspired human observation for generations. By understanding the Moon's early rotation, we gain not only a deeper appreciation for its present stability, but also insight into the broader mechanisms that govern the motion of celestial bodies throughout the universe, a dance of gravity, inertia, and time that continues silently above us. The relationship between the Earth and Moon is not a static one. It is an ongoing dialogue of energy and motion, a subtle exchange that has persisted for billions of years. At the heart of this exchange lies the concept of angular momentum, a measure of rotational motion that is conserved in isolated systems. As the Moon orbits the Earth, tidal forces raise bulges on both bodies, with the gravitational pull slightly misaligned relative to the line connecting their centers of mass. These tidal bulges act as levers, transferring angular momentum from the Earth's rotation to the Moon's orbital motion, a process that gradually pushes the Moon farther away, while simultaneously slowing the Earth's spin. This delicate transfer is the reason why the length of our day is increasing ever so slightly over geological time, and why the Moon retreats from our planet at a measurable pace. Modern science has been able to quantify this recession with extraordinary precision. NASA's Lunar Laser Ranging experiments, initiated in 1969 with retroreflectors left on the lunar surface by Apollo astronauts, involve sending laser pulses from Earth and timing their return after bouncing off these reflectors. Measurements have confirmed that the Moon is receding at an average rate of approximately 3.8 centimeters per year. While this may seem minuscule, over millions of years it accumulates to significant distances, illustrating the long-term effects of tidal interaction and energy transfer. The experiments not only confirm the predictions of tidal theory, but also provide an exquisite laboratory for testing the principles of orbital mechanics and gravitational dynamics in a real-world system. The concept of tidal lag is central to understanding how energy is dissipated in the Earth-Moon system. As the Earth rotates faster than the Moon orbits, the tidal bulges on Earth are carried slightly ahead of the Moon, creating a torque that transfers rotational energy from Earth to the Moon. On the lunar side, although the Moon's rotation is now synchronized with its orbit, tidal flexing of its interior continues to dissipate energy as heat. This internal friction, occurring within the Moon's mantle and crust, was studied in detail by astrophysicists such as Richard Ray and Clifford Will, who modelled the long-term effects of energy dissipation on orbital stability. Their work demonstrated how even minor internal deformations, sustained over billions of years, are sufficient to maintain the Moon's orientation and reinforce the stability of its synchronous rotation. The transfer of angular momentum and the resulting energy redistribution have profound implications for the stability of the Moon's face toward Earth. As the Moon's orbit expands and its rotation remains locked, the system achieves a dynamic equilibrium. Small perturbations in orientation or orbital speed are corrected naturally through the ongoing action of tidal torques, ensuring that the same hemisphere of the Moon remains visible from our planet. This self-correcting mechanism highlights the elegance of gravitational physics, a balance achieved through the interplay of rotational energy, orbital motion, and internal dissipation, producing a configuration that is stable on timescales far exceeding human history. The dynamics of energy transfer between the Earth and Moon also offer insight into broader planetary processes. Tidal interactions are a common feature of planetary systems, influencing the spin and orbit of moons around gas giants, and even affecting the rotation of exoplanets in close orbit around their stars. By examining the Earth-Moon system, scientists gain a tangible example of how these principles operate in practice, providing a model that can be applied to distant and otherwise inaccessible systems. Observations of partial tidal locking, eccentric orbits, and spin-orbit resonances elsewhere in the solar system illustrate the variety of outcomes that arise from similar underlying forces, emphasizing the universality of these gravitational processes. These energy exchanges are gentle in the immediate sense, almost imperceptible from one day to the next, yet they accumulate with extraordinary effect over geological time. The Moon's gradual recession and the subtle slowing of Earth's rotation demonstrate that even seemingly modest forces, acting consistently, can reshape the dynamics of entire planetary systems. The process is not linear or uniform. Variations in ocean depth, mantle composition, and orbital eccentricity modulate the efficiency of energy transfer, producing a nuanced and dynamic interaction that is constantly in flux while maintaining overall stability. Tidal bulges themselves serve as a visible manifestation of this cosmic negotiation. On Earth, the high and low tides provide a daily rhythm, a reminder of the Moon's persistent influence, while on the Moon, the flexing of rock beneath its surface operates silently, invisible yet equally consequential. The study of these bulges, both terrestrial and lunar, offers critical insights into the mechanics of tidal friction, torque, and angular momentum transfer, linking observable phenomena to fundamental principles of physics. Institutions such as NASA, the European Space Agency, and observatories worldwide continue to monitor these interactions, refining our understanding of how small forces produce large, cumulative effects. Understanding the Earth-Moon energy exchange also allows for fascinating reflections on time and scale. While humans perceive the Moon as constant and unchanging, it is in reality part of a slow, measured process of evolution that spans billions of years. Each centimetre the Moon recedes, each fraction of a millisecond added to the length of a day, represents countless interactions, countless flexes of rock and ocean, patiently guiding the system toward equilibrium. This awareness deepens our appreciation of the Moon not merely as a visual companion in the night sky, but as an active participant in a dynamic gravitational relationship, a silent partner in a dialogue of energy, momentum, and time. By considering these interactions, we see that the Moon's stability and the predictability of its orientation are products of subtle, ongoing processes. The energy exchange through tidal bulges and the gradual transfer of angular momentum has created a configuration that is remarkably resilient, maintaining the familiar lunar face we observe and preserving the delicate balance of the Earth-Moon system. It is a dance of forces, invisible yet undeniable, whose rhythm has been maintained for billions of years, a testament to the power of gentle, persistent physical laws in shaping the cosmos. Beneath the serene surface of the Moon lies a layered world, each stratum responding differently to the subtle tug of Earth's gravity. The crust, composed primarily of rigid, rocky material, forms the outermost shell, averaging about 30 to 50 kilometers in thickness. Beneath it, the mantle extends for several hundred kilometers, composed of partially molten and solid rock capable of slow, plastic flow under stress. At the Moon's core, scientists believe there exists a small, dense metallic region, roughly 300 kilometers in radius, possibly containing iron mixed with lighter elements. Each of these layers exhibits distinct rigidity and elasticity, influencing how the Moon deforms under tidal forces and consequently how energy is dissipated internally. The Gravity Recovery and Interior Laboratory, or GRAIL mission, launched by NASA in 2011, provided unprecedented insight into these internal properties. By precisely measuring variations in the Moon's gravitational field, GRAIL revealed subtle anomalies that correlate with differences in crustal thickness and density, highlighting areas where the Moon's interior is more or less capable of flexing under stress. These gravitational variations allow scientists to infer how energy from tidal interactions is distributed throughout the Moon's interior, giving a detailed picture of how the satellite absorbs and dissipates forces that would otherwise alter its rotation. Understanding this energy dissipation requires considering the Moon as a viscoelastic body, a concept explored in detail by Walter Munk and George MacDonald in the mid-20th century. Viscoelastic models describe how solid materials can exhibit both elastic and viscous behavior, bending or stretching under force while also dissipating energy as heat. In the Moon, tidal bulges raised by Earth's gravity deform the crust and mantle slightly, generating friction that converts rotational energy into thermal energy. This process is slow and subtle, imperceptible on human timescales, but over millions and billions of years, it produces measurable changes in rotation and orbital dynamics, guiding the Moon toward its current synchronized state. Internal friction is particularly important because it links the Moon's structural properties directly to the long-term evolution of its rotation. The rigidity of the crust resists deformation, producing a delayed response to Earth's gravitational pull, while the mantle's partial plasticity allows energy to be absorbed and redistributed internally. The resulting tidal lag generates torques that gradually slow the Moon's spin, transferring angular momentum and contributing to the maintenance of synchronous rotation. Without this internal viscoelastic response, the Moon might not have achieved the precise alignment observed today, and the stability of the familiar lunar face could be far less assured. The influence of internal structure extends beyond rotation to the Moon's orbital behavior. By determining how effectively tidal energy is dissipated, the Moon's composition shapes the rate at which it recedes from Earth and the timescale over which tidal locking is maintained. Regions of higher density or rigidity can concentrate stress and heat, producing localized effects on libration and orbital eccentricity, while more pliant regions facilitate smoother energy transfer. Through the combination of crustal strength, mantle plasticity, and core dynamics, the Moon achieves a balance that preserves both its orientation and its distance, maintaining the delicate equilibrium that characterizes the Earth-Moon system. Observations from the Grail mission, complemented by lunar seismic data collected during the Apollo program, allow scientists to model these processes with extraordinary precision. By inputting measured variations in crustal thickness, mantle composition, and core properties into viscoelastic simulations, researchers can predict how the Moon responds to tidal forces at different depths and over extended timescales. These models confirm that internal friction is a primary driver of rotational energy loss, converting slow mechanical motion into heat and stabilizing the Moon's spin. The intricate interplay between structure and tidal response demonstrates how even subtle internal properties can have profound effects on the dynamics of a celestial body. The Moon's internal response is not uniform, and subtle variations produce complex behaviors. For example, the near side of the Moon, which faces Earth, has a thinner crust compared to the far side, allowing slightly more flexing under tidal stress. This asymmetry influences the distribution of heat and the efficiency of energy dissipation, subtly shaping the Moon's libration and orbital evolution. Over geological time, these small differences accumulate, contributing to the precise alignment that characterizes tidal locking. In this way, the internal structure serves as both a buffer and a mediator, absorbing energy while preserving stability. By understanding the Moon's internal layers and their viscoelastic properties, we gain a deeper appreciation for how energy transfer, friction, and structural composition work together to maintain long-term orbital dynamics. The Moon's rotation, its synchronized face, and the stability of its orbit are all products of this invisible, patient process. Each flex of rock, each subtle deformation, represents a tiny contribution to a cumulative effect that spans billions of years, illustrating how internal structure shapes the evolution of celestial bodies. Through careful study of the crust, mantle, and core, scientists reveal the hidden mechanisms that sustain the Moon's calm presence in the sky, a testament to the intricate and elegant balance of forces at work within our closest celestial neighbour. Although the Moon always shows the same general face to Earth, careful observation reveals subtle oscillations, tiny shifts that allow us to glimpse slightly more than half of its surface over time. These motions, known collectively as librations, are caused by a combination of orbital eccentricity, axial tilt, and the Moon's internal flexibility. There are three primary types of libration that astronomers describe: longitudinal, latitudinal, and diurnal. Longitudinal libration arises from the Moon's elliptical orbit, causing it to move slightly faster or slower at different points along its path around Earth, allowing observers to see beyond the eastern and western edges of the near side. Latitudinal libration results from the tilt of the Moon's rotational axis relative to its orbital plane, enabling a gentle nodding that reveals areas near the north and south poles. Diurnal libration is caused by the daily rotation of Earth, creating a small apparent shift as the observer's viewpoint changes over the course of a night. Together, these motions increase the portion of the lunar surface visible from Earth to approximately 59%, expanding our view beyond the nominal hemisphere. Understanding and measuring libration has been a long-term pursuit for astronomers, and it has benefited from the contributions of lesser-known but remarkable scientists such as Eleanor Helin. Helin, an American astronomer active during the mid-20th century, focused on tracking minor variations in the positions and rotations of celestial bodies, including subtle lunar motions. Her work helped refine models of lunar libration, demonstrating that even seemingly imperceptible shifts can reveal critical insights about internal structure, orbital dynamics, and the history of tidal interactions. By analysing the moon's oscillations over extended periods, Helin and her colleagues contributed to our understanding of how rotational synchronization is maintained, and how tidal forces continue to subtly influence the moon's behaviour today. The mechanics behind libration are closely linked to the moon's internal structure and its response to tidal forces. The slight flexing of the crust and mantle under the influence of Earth's gravity allows the moon to adjust to variations in orbital speed and alignment. This internal compliance, combined with the orbital eccentricity of approximately 0.05, produces the gentle rocking motion that we observe as longitudinal libration. Similarly, the tilt of the moon's axis, about 6.7 degrees relative to its orbital plane, permits latitudinal nodding. Even the small shifts caused by the rotation of Earth, contributing to diurnal libration, depend on the interplay between observer perspective and the moon's orientation. Together, these factors illustrate how both the internal and external properties of the moon collaborate to produce the familiar yet subtly shifting view we enjoy from our planet. Observing libration provides a more nuanced understanding of the lunar surface. Over time, as the moon rocks slightly back and forth, regions near the edges of the near side come into view, revealing additional craters, highlands, and mare formations. This expanded visibility has allowed astronomers to map surface features more completely and to identify patterns in crater distribution, volcanic plains, and tectonic structures. By comparing the visible near side to the previously hidden far side, first photographed by the Soviet Luna 3 spacecraft in 1960, scientists have gained insight into asymmetries in crustal thickness and mantle composition. Libration thus acts as a natural window, offering glimpses beyond the hemisphere that remains constantly oriented toward Earth, enriching our understanding of lunar geology and history. The visual experience of libration can be imagined as a slow, measured rocking, almost like a pendulum swinging with an imperceptible rhythm. The moon tilts slightly, rocks gently east and west, nods to reveal the polar regions, and shifts subtly as Earth turns beneath it. These motions are so subtle that casual observation might not notice them from one night to the next, yet over weeks and months the effect becomes apparent, allowing careful observers to chart more of the lunar surface. This imagery helps to conceptualize the dynamic nature of tidal locking, revealing that even in a state of synchronous rotation, the moon retains a small degree of flexibility and motion that speaks to the enduring influence of gravitational interactions. Libration also underscores the connection between rotational dynamics and orbital stability. By observing how the moon adjusts to its slightly elliptical orbit and axial tilt, astronomers can infer the presence of tidal torques and energy dissipation within the interior. These measurements inform models of angular momentum transfer, showing how rotational energy is gradually converted into heat, stabilizing the moon's spin while allowing minor oscillations to persist. In essence, libration provides tangible evidence of the ongoing balance between rigidity and flexibility, energy and motion, that characterizes the Earth-Moon system. In addition to its scientific significance, libration enriches our aesthetic and cultural perception of the moon. It is the reason we can glimpse a few craters near the edges that would otherwise remain hidden, offering a sense of variety and discovery in an otherwise familiar celestial companion. Through both telescopic observation and photographic imaging, these gentle motions reveal that the moon, while tidally locked, is far from static. It is engaged in a quiet, dynamic dialogue with Earth, responding to gravitational pulls and rotational constraints with subtle elegance, a cosmic rhythm that is as precise as it is graceful. By studying lunar libration, scientists have gained insight into the timing and scale of tidal locking, the distribution of mass within the moon, and the long-term evolution of its orbit. The gentle oscillations observed provide evidence that even after billions of years of gravitational interaction, the moon retains flexibility and responsiveness, maintaining its orientation while subtly revealing additional terrain. This dynamic behavior highlights the interplay of physics, geology, and orbital mechanics, and serves as a reminder that what appears constant and unchanging in the night sky is, in reality, a careful balance of forces operating over immense spans of time. Through the lens of libration, the moon emerges not only as a familiar face in the sky, but as a living, responsive participant in the ongoing cosmic dance with Earth. The phenomenon of tidal locking is not unique to our moon. It is a common feature throughout the solar system, shaping the behavior of countless moons and other celestial bodies. Jupiter's moon Io, for example, is a striking illustration of how tidal forces can create dynamic, even violent activity. Locked in synchronous rotation with its orbit around Jupiter, Io experiences immense tidal flexing due to its slightly eccentric orbit and the gravitational pull of neighbouring moons, including Europa and Ganymede. This continual flexing generates frictional heat within Io's interior, driving the most active volcanism in the solar system. Rivers of molten lava erupt across its surface, a dramatic reminder that tidal locking does not equate to stillness. It can create internal energy that manifests in astonishing geological activity. Europa, another of Jupiter's moons, is similarly locked to its planet, maintaining the same face toward Jupiter as it completes its orbit roughly once every 3.5 Earth days. Its icy crust is believed to float atop a subsurface ocean, heated in part by tidal forces acting upon the moon's interior. This tidal heating produces cracks, ridges, and geysers of water vapor, and it has profound implications for the potential habitability of the ocean below. Saturn's moon, Enceladus, also demonstrates the power of tidal heating, erupting plumes of water and ice from its south polar region. Locked in synchronous rotation with Saturn, Enceladus's interior experiences repeated stretching and flexing, generating heat sufficient to maintain liquid reservoirs beneath an icy shell. These examples show that tidal locking is not merely a static alignment, but a driver of internal activity, influencing geology, thermal dynamics, and potentially even astrobiology. The study of these interactions has been greatly informed by the work of astrophysicists such as Matija Cuk, who has explored spin-orbit resonances and the broader dynamics of tidally influenced moons. Chuk's research examines how the distribution of mass, orbital eccentricity, and resonance relationships with neighbouring bodies can affect the efficiency and stability of tidal locking. For instance, Io's intense volcanism is amplified by the gravitational interplay with Europa and Ganymede, creating a resonant chain that maintains orbital eccentricity and enhances tidal heating. These complex interactions highlight the fact that tidal locking is not an isolated phenomenon. It exists within a network of gravitational relationships, with each body influencing and responding to the others over vast periods of time. When comparing the orbital periods and rotation rates of different moons, a pattern emerges. Many of the large satellites in the solar system, from the Galilean moons of Jupiter to Titan orbiting Saturn, display synchronous rotation with their parent planets. The periods range from a few Earth days for small, close-in moons to tens of Earth days for more distant satellites, yet the underlying principle remains consistent. Tidal forces gradually synchronize rotation with orbital motion. This regularity demonstrates the universality of tidal locking, suggesting that similar processes are at work in countless planetary systems, both near and far. Observing these moons provides a natural laboratory for understanding how gravitational torques, energy dissipation, and angular momentum exchange operate in diverse contexts. The implications extend beyond our own solar system to exoplanetary research. Planets orbiting close to their stars, particularly in tightly packed systems, or around dimmer red dwarf stars, are likely to become tidally locked over geological timescales. In these systems, one hemisphere permanently faces the star while the other remains in perpetual night, creating extreme environmental conditions and influencing atmospheric circulation. By studying the moons in our own celestial neighbourhood, astronomers can develop models to predict how tidal locking will affect distant exoplanets, offering insight into climate patterns, habitability, and planetary evolution. The physics that governs the Moon and its cousins thus becomes a universal tool for understanding worlds light years away. Tidal locking also demonstrates the elegance and predictability of celestial mechanics. While each moon is unique in composition, size, and orbital characteristics, the same fundamental principles, gravitational attraction, energy dissipation, and angular momentum transfer, govern their behavior. Observations of synchronous rotation across a variety of moons confirm theoretical models, showing that over millions or billions of years, tidal forces reliably bring rotating bodies into alignment with their orbits. Even small variations in orbital eccentricity or internal composition can create fascinating consequences, such as Io's volcanism or Europa's icy fractures, illustrating the diversity of outcomes within a unified physical framework. The visual and conceptual experience of tidal locking in these moons can be imagined as a series of dances moving in rhythm with an unseen partner. Each moon rotates just enough to keep one face toward its planet, yet beneath the surface, internal motions and energy flows create hidden activity, like a dancer flexing muscles and adjusting balance while maintaining perfect synchronization. This metaphor captures both the stability and the dynamism of tidally locked bodies, emphasizing that apparent stillness is often accompanied by subtle but powerful internal motion. It is a reminder that in the universe, equilibrium and activity are not mutually exclusive but are often intertwined. By studying these moons, scientists can trace the interplay between rotational dynamics, orbital eccentricity, and internal structure. The efficiency of tidal locking, the magnitude of tidal heating, and the stability of orientation all depend on how mass is distributed, how flexible the interior is, and how external gravitational influences interact. Observational campaigns using spacecraft such as Galileo, Cassini, and Juno have provided high-resolution imagery, gravity measurements, and magnetic field data, allowing detailed models that connect surface phenomena to internal and orbital mechanics. Through these studies, the principles observed in the Moon are shown to apply widely, reinforcing the idea that tidal locking is a natural and inevitable outcome of gravitational interaction in many planetary systems. Ultimately, the study of Io, Europa, Enceladus, and other tidally locked moons emphasizes the universality of the phenomenon. Whether it manifests as a volcanic inferno, a frozen ocean with erupting geysers, or a stable, calm lunar surface, tidal locking shapes the behavior and evolution of moons across the solar system. The Moon's familiar face is just one example of a widespread process, a testament to the power of gravitational forces operating over immense timescales. By observing and modeling these bodies, scientists gain a profound understanding of the delicate balance between rotation, orbit, and internal dynamics, a balance that orchestrates the cosmic dance of moons and planets alike. Not all moons or planets achieve perfect tidal locking, and in many cases bodies remain only partially synchronized with their orbits. This partial locking occurs when the gravitational forces exerted by the host planet or star are insufficient to completely match the rotation of the satellite to its orbital period, or when the orbital path itself is highly eccentric. In these situations, the body may exhibit complex rotational behavior, including wobbling, periodic variations in spin rate, or temporary spin-orbit resonances, in which the rotational period becomes a simple fraction of the orbital period rather than an exact match. These partially locked states demonstrate that tidal locking is not a simple yes or no outcome, but a process influenced by multiple factors, including mass, distance, internal structure, and orbital eccentricity. Cassini states provide an important framework for understanding how partially locked bodies maintain a stable orientation over time. Named after the Italian astronomer Giovanni Domenico Cassini, these states describe a configuration in which the spin axis of a moon or planet is tilted at a fixed angle relative to its orbit, while precessing in a synchronized manner with the orbital plane. A body in a Cassini state can maintain a consistent tilt even as its orbit evolves, and this configuration can stabilize a partially locked rotation. Resonance capture theory further explains how a body might become trapped in one of these states during the early stages of rotational evolution. As the rotation slows under tidal forces, small perturbations in the orbit or internal dissipation can guide the body into a resonant spin, locking it temporarily or indefinitely in a configuration that balances gravitational torques and angular momentum. Eccentricity-driven variations add another layer of complexity. When an orbit is not perfectly circular, the distance between the satellite and its host fluctuates over time, causing the gravitational pull to vary. This variation can produce a small but persistent torque on the spinning body, generating librations or oscillations in rotation. In some cases, these oscillations are large enough that the body never achieves perfect synchronous rotation, instead alternating between slightly faster and slower spin rates, while still remaining generally aligned with its orbital motion. Such behavior is observed in some of the smaller moons of Saturn and Jupiter, and it is also predicted for exoplanets orbiting close to their parent stars in eccentric orbits. The combination of eccentricity, tidal dissipation, and internal structure determines whether a body will settle into full locking, partial locking, or even chaotic rotation. Astrophysicists such as Rory Barnes and Jacques Lasker have explored these processes in detail. developing models that quantify the timescales and stability of tidal locking across a wide range of celestial bodies. Their work demonstrates that factors such as planetary mass, orbital eccentricity, and rotational inertia all influence how efficiently tidal forces can synchronize spin and orbit. In some systems, a small increase in eccentricity or internal viscosity can dramatically alter the outcome, leading to long-lived partial locking rather than full synchronization. By comparing theoretical models with observational data from moons, planets, and exoplanets, researchers can test the universality of tidal interactions and refine predictions about the evolution of rotational states in different environments. In contrast, the Earth-Moon system represents a particularly stable configuration. The Moon's relatively circular orbit, modest eccentricity of approximately 0.05, and internal composition contribute to a robust tidal interaction that has successfully synchronized its rotation with its orbit. The Earth's gravitational pull produces consistent tidal bulges, and the Moon's viscoelastic interior efficiently dissipates energy, maintaining the synchronous rotation that we observe today. Small oscillations known as librations persist, but they do not disrupt the overall stability of the system. This equilibrium is a result of billions of years of cumulative interactions during which the Moon gradually lost rotational energy while transferring angular momentum to its orbit, reaching a state that is both predictable and enduring. Partial tidal locking and resonance capture illustrate the dynamic nature of celestial mechanics. They reveal that even within a system dominated by gravitational forces, subtle variations can produce a spectrum of outcomes, from perfect synchronous rotation to quasi-stable spin states and intermittent oscillations. Observations of these behaviors provide insight into the interplay between spin, orbit, and internal structure, demonstrating that tidal locking is a process shaped by time, energy dissipation, and the delicate balance of forces. This understanding allows scientists to apply lessons learned from the Earth-Moon system to a diverse array of moons, planets, and exoplanets, offering a universal framework for predicting rotational behavior under tidal influence. By imagining these processes, one can visualize a variety of moons and planets, each spinning at its own rate, some fully synchronized, some wobbling slightly, and some captured in a resonant rhythm. Each system represents a balance of gravitational forces and internal response, with energy slowly shifting from rotation to orbital motion or internal heat. In this cosmic ballet, the Earth-Moon system stands out as a particularly harmonious duet. Where the Moon's face remains constant, rotation and orbit are synchronized, and the subtle influence of tides has produced a stable, enduring partnership. Meanwhile, elsewhere in the solar system and beyond, other bodies continue their own intricate dances, revealing the universality of tidal locking and the richness of rotational dynamics across the cosmos. The study of variations in tidal locking and resonance states not only illuminates the Moon's history, but also informs our understanding of exoplanetary systems. Planets orbiting close to their stars, particularly in compact systems or around dimmer red dwarf stars, are likely to experience partial locking or resonance capture, with implications for climate, atmospheric dynamics, and potential habitability. By observing moons like Io, Europa, and Enceladus, and by modeling these processes theoretically, scientists gain a framework for predicting rotational and orbital behavior in distant systems. These insights underscore the importance of tidal interactions, eccentricity, and internal response as fundamental factors shaping the motion of celestial bodies across the universe, from familiar moons in our own backyard to planets light years away. The Moon's influence extends far beyond its silent vigil in the night sky. It plays a vital role in shaping conditions on Earth that support life. One of the most immediate and visible effects is on the tides. By raising oceanic bulges through its gravitational pull, the Moon generates rhythmic high and low tides that have been a constant feature of the Earth's coastal environments for billions of years. These tides created dynamic habitats along shorelines where pools of water would rise and fall, exposing and submerging nutrients, sediments, and organisms. It is in these intertidal zones that early life likely found opportunities for adaptation and evolution, shaping ecosystems in ways that persist even today. Beyond the influence on water, the Moon contributes to climate stability through its effect on Earth's axial tilt, or obliquity. The axial tilt determines the intensity of seasonal variation and the distribution of solar energy across the planet. Without the stabilizing gravitational influence of the Moon, Earth's tilt could vary chaotically over hundreds of thousands to millions of years, producing extreme shifts in climate that would have profound consequences for the evolution of life. By providing a stabilizing torque on the Earth's rotation, the Moon helps maintain an obliquity of approximately 23.4 degrees, a tilt that supports moderate seasons and long-term environmental predictability, crucial factors for the development of complex ecosystems and the emergence of life on land. Astrobiology research, such as that conducted by Brian J.P. Copeland, explores these connections between planetary dynamics and habitability. Studies indicate that stable tidal forces and a consistent axial tilt create conditions conducive not only to liquid water and moderate climates, but also to predictable environmental cycles that life can adapt to. Organisms, from the simplest tidal organisms to complex terrestrial plants and animals, have evolved biological rhythms, circadian and circadial cycles, that align with these predictable patterns. The Moon's role in shaping these rhythms illustrates the profound interconnectedness of celestial mechanics and biological systems, linking the movement of distant objects in space to the timing of life on Earth. Tidal stability also impacts human perception and culture. Across millennia, humans have observed the rise and fall of tides, noting the connection to lunar phases. Early agricultural societies used these observations to guide planting and harvesting, while coastal communities relied on the predictability of tides for fishing and navigation. The Moon's influence on biological and ecological rhythms provided a natural framework for early calendars and societal organization, illustrating a subtle but enduring link between celestial forces and human activity. This relationship demonstrates that the Moon's tidal effects extend beyond physical mechanics, shaping behavior, culture, and understanding in ways that continue to resonate today. The energy transferred through tides has geological consequences as well, subtly modifying the rotation of Earth and its orbital dynamics. Tidal friction gradually dissipates rotational energy, slowing the Earth's spin over geological time. This slowdown lengthens the day by approximately 1.7 milliseconds per century, a seemingly minor effect that nonetheless influences climatic patterns and the synchronization of biological processes with diurnal cycles. By creating predictable environmental rhythms, the Moon indirectly supports the evolutionary stability of ecosystems, reinforcing the link between celestial mechanics and life's adaptation. Moreover, the Moon's presence has consequences for both coastal and global ecology. Intertidal zones, estuaries, and shallow marine habitats rely on the regularity of tidal flux, which distributes nutrients, oxygenates water, and supports diverse food webs. Even in modern times, the influence of tides affects fisheries, sediment transport, and coastal erosion. By modulating these processes with a rhythmic regularity, the Moon has contributed to the development of ecological niches that foster biodiversity. Its gravitational influence serves as a stabilizing force in both physical and biological systems, highlighting the deep interconnection between planetary mechanics and life's persistence. From a planetary perspective, the Earth-Moon relationship serves as a model for understanding habitability elsewhere in the universe. Researchers studying exoplanets recognize that moons can stabilize a planet's tilt and moderate climate, enhancing the potential for life. Observations of tidal locking, axial stabilization, and orbital dynamics inform models of planetary environments far beyond our solar system, demonstrating that the principles observed here are universal. The Moon's quiet, persistent influence thus offers insight into the conditions necessary for life, illustrating that celestial mechanics and biology are not separate domains, but parts of a continuous interwoven system. By contemplating the Moon's effect on tides, climate, and biological rhythms, one begins to appreciate the intricate balance that makes Earth uniquely hospitable. Its gravitational pull regulates oceans, its stabilizing torque preserves the orientation of the planet, and its rhythmic presence shapes the very timing of life on land and sea. The Moon's influence is both subtle and profound, demonstrating that even distant, unseen forces have tangible consequences for ecosystems, evolutionary processes, and human observation. In this sense, the familiar face we see in the night sky is not merely a companion in darkness, but an active participant in the creation and maintenance of the environment that supports life on our planet. Beyond the familiar mechanics of tidal locking lies a deeper, more intricate layer of celestial dynamics, where spin-orbit resonance, chaotic rotation, and orbital instabilities combine to create a rich tapestry of motion. Spin-orbit resonance refers to a condition in which a body's rotational period forms a simple fractional relationship with its orbital period rather than achieving full synchronous rotation. Mercury, for instance, rotates 3 times for every 2 orbits around the Sun, an example of a 3-to-2 spin-orbit resonance. While the Moon has reached a simple 1-to-1 resonance with Earth, understanding higher-order resonances provides insight into the complex interplay between gravitational forces, internal dissipation, and orbital eccentricity. These resonances demonstrate that tidal locking is not a singular outcome, but part of a continuum of possible rotational states shaped by the forces acting over billions of years. Chaotic rotation and orbital instability further complicate this picture. In systems with multiple interacting bodies or significant eccentricities, small perturbations can produce unpredictable changes in rotation and orbit. In the early Earth-Moon system, for example, the Moon's orbit was likely more eccentric and subject to irregularities caused by gravitational interactions with other protoplanetary material and the Sun. Such conditions could have produced short periods of chaotic spin, in which the Moon's rotation varied non-linearly and unpredictably. Yet these chaotic phases were gradually dampened by tidal friction and energy dissipation. The result is the steady, predictable orientation we observe today. But it is important to recognize that the path to this equilibrium was not smooth. Even slight shifts in eccentricity or axial tilt could have temporarily disrupted rotational stability, illustrating the sensitivity of orbital evolution to initial conditions and external influences. Jacques Lascar, a prominent French astrophysicist, has devoted significant effort to modeling long-term planetary evolution, employing numerical simulations to explore the dynamics of the solar system over hundreds of millions of years. His work demonstrates that planetary and satellite orbits are subject to subtle instabilities that can be amplified over geological time. By calculating the effects of perturbations from neighboring planets, variations in orbital eccentricity, and spin-orbit interactions, Lascar's models reveal that the Earth-Moon system, while remarkably stable today, likely experienced episodes of orbital flux and rotational adjustment in its early history. These findings highlight the fact that even in a system we now perceive as calm and predictable, complex forces acted to shape trajectories, energy distribution, and rotational behavior long before the Moon settled into synchronous rotation. High eccentricity effects in the early Earth-Moon system played a pivotal role in shaping both rotation and orbital dynamics. If the Moon's initial orbit deviated significantly from circularity, the resulting variations in gravitational force would have produced fluctuating tidal torques, inducing rotational acceleration and deceleration, as well as slight variations in orientation relative to Earth. These effects would have enhanced energy dissipation within the Moon's interior and across its tidal bulges, gradually reducing eccentricity and stabilizing rotation. Over time, the cumulative action of tidal friction, angular momentum exchange, and orbital alignment led to the 1-to-1 resonance we observe today. Understanding these early instabilities is crucial, as they reveal that tidal locking is not merely the product of simple, steady forces, but of a dynamic process responding to both initial conditions and continuous perturbations. At a systems level, the interactions between spin, orbit, and internal structure illustrate the interconnectedness of planetary mechanics. The Moon's rotational behavior cannot be considered in isolation. It is the product of gravitational forces from Earth, the Sun, and to a lesser extent other planetary bodies, modulated by the Moon's internal structure and tidal dissipation properties. Models of spin-orbit resonance and chaotic rotation show that even small differences in mass distribution, rigidity, or orbital eccentricity can produce divergent evolutionary paths, highlighting the sensitivity of celestial systems to initial parameters. In this context, the Earth-Moon system represents an exceptionally well-tuned configuration, where early instabilities were gradually corrected by tidal interactions, producing the stable synchronous rotation we observe today. The application of these high-level theoretical perspectives extends beyond our own Moon. Exoplanets orbiting close to their stars may become tidally locked in similar ways, and their rotation can be influenced by eccentricity, multiple stellar companions, or resonances with nearby planets. Spin-orbit resonance models help predict these outcomes, indicating which planets may exhibit permanent day and night sides, chaotic rotation, or intermediate states. Laska's methods, combining numerical simulation and long-term perturbation analysis, provide a framework for understanding how even minor variations in mass or orbit can influence rotational stability across billions of years. These principles reinforce the universality of tidal dynamics and the predictive power of celestial mechanics in diverse planetary systems. Visualizing these processes can be aided by imagining the Moon as a pendulum, initially swinging with irregular amplitude and direction, buffeted by the gravitational pulls of Earth and the Sun. Over time, friction within its interior acts as a damping mechanism, gradually reducing chaotic motion and aligning the swing with the orbital rhythm. Spin-orbit resonance represents a stabilized fraction of this swing, while high eccentricity periods correspond to the larger uneven oscillations. As energy dissipates and torques adjust the Moon's rotation, the system evolves toward equilibrium. This analogy captures both the dynamism and the subtlety of celestial mechanics, showing that even in apparent stillness, the Moon has experienced a complex dynamic journey to its present orientation. The interplay of chaotic rotation, resonance, and long-term orbital evolution highlights the delicate balance maintained in planetary systems. Tidal forces, angular momentum conservation, and energy dissipation are universal principles, yet their effects are mediated by each body's internal structure, orbital characteristics, and gravitational environment. By considering these high-level theoretical perspectives, we gain a more comprehensive understanding of the Moon's rotational history, the processes that led to tidal locking, and the broader context of spin-orbit dynamics across the universe. It is a systems-level view that reveals the Moon not simply as a passive companion, but as an active participant in a complex, ongoing interaction, shaped by forces that operate over unimaginable timescales and vast cosmic distances. Through this lens, we can appreciate that the Moon's present stability is both remarkable and delicate, the product of billions of years of adjustment, energy transfer, and orbital refinement. The high eccentricity phases, chaotic rotation episodes, and resonant interactions of its early history laid the foundation for the synchronous rotation that defines its familiar face. By studying these mechanisms, scientists are able to extend their understanding to other moons, planets, and exoplanets, predicting rotational states, tidal heating, and orbital evolution across the cosmos. In this way, the Moon serves as a local example of universal principles, demonstrating the intricate and elegant balance of forces that govern celestial bodies and the dynamic systems they inhabit. One of the most striking features of the Moon is the asymmetry between its near side, which constantly faces Earth, and its far side, hidden from human eyes, until the Soviet Luna 3 spacecraft transmitted the first images in 1960. The far side is dominated by a thick, rugged crust, averaging roughly 60 kilometers in depth, compared to the thinner, smoother crust of the near side, which averages about 30 kilometers. This difference influences both the topography and gravitational field of the Moon, producing subtle anomalies detected by missions such as NASA's Grail spacecraft. The far side is heavily cratered and largely devoid of the dark volcanic plains, or maria, that characterize the near side, creating a visual and structural dichotomy that has intrigued scientists for decades and provided crucial clues about the Moon's formation and internal evolution. The most widely accepted explanation for the Moon's origin is the giant impact hypothesis, championed by scientists such as William K. Hartmann and Eric Asphaug. According to this theory, a Mars-sized body, often called Theia, collided with the proto-Earth approximately 4.5 billion years ago. The enormous energy of the impact ejected debris into orbit, which eventually coalesced to form the Moon. This model accounts for several key observations, including the similarity of isotopic compositions between Earth and lunar rocks, the relatively small iron core of the Moon, and the asymmetry in crust thickness. Hartmann and Asphaug emphasized that the impact dynamics, combined with subsequent tidal interactions, could have led to preferential distribution of molten material on the near side, producing the widespread maria while leaving the far side crust thick and relatively undeveloped. Alternative hypotheses, such as the capture theory, proposed that the Moon formed elsewhere in the solar system and was later gravitationally captured by Earth. This idea, while historically considered, faces challenges in explaining the isotopic similarities and the precise orbital configuration of the Moon. Nevertheless, capture scenarios and hybrid models have persisted in scientific discourse, particularly when addressing anomalies that are not fully explained by the giant impact hypothesis. Researchers continue to examine these alternative perspectives, comparing isotopic data, orbital dynamics, and geophysical measurements to test the plausibility of various formation mechanisms. Anomalies such as the far side's elevated crust, the distribution of mass concentrations known as mascons, and the asymmetric arrangement of Maria inform and challenge existing models. Mascons, discovered in the 1960s through gravitational studies of lunar orbiters, represent regions of concentrated mass beneath the surface that influence satellite orbits and contribute to minor libration effects. These features suggest that the Moon's internal structure is heterogeneous, and their distribution supports the notion that the Moon's formation involved both violent collisions and subsequent differentiation of materials. By studying these anomalies, scientists gain insight into the thermal and mechanical evolution of the Moon, as well as the complex interactions between impact processes, volcanic activity, and tidal forces. The ongoing debates surrounding lunar origin illustrate the evolving nature of scientific understanding. As new data emerge from missions such as Lunar Reconnaissance Orbiter and GRAIL, previous assumptions are revisited, refined, or occasionally overturned. The scientific process thrives on this iterative approach, where competing theories are tested against observational evidence and models are continually improved. Each anomaly, from crust thickness variations to subtle gravitational irregularities, is not merely an oddity, but a clue, a piece of the puzzle that guides researchers toward a more complete picture of the Moon's history. This dynamic discourse highlights the importance of remaining open to alternative explanations and the value of integrating multiple lines of evidence, from geochemistry to orbital mechanics, in constructing robust scientific models. Visualizing the consequences of these anomalies can help contextualize their significance. Imagine the Moon as a sculpted globe with uneven density, its near sides smoothed by molten basalt, filling massive impact basins, while the far side remains rough and elevated, a silent record of ancient collisions. As spacecraft and telescopic observations measure gravitational perturbations, thermal variations, and surface features, these subtle differences reveal the interplay between formation processes and long-term orbital evolution. Even minor irregularities in crustal thickness can influence tidal flexing, rotational stability, and energy dissipation, demonstrating that internal structure is inseparable from the Moon's broader celestial behavior. These considerations also illuminate broader principles in planetary science. The study of lunar anomalies informs our understanding of satellite formation, planetary differentiation, and the dynamics of tidal locking. By analyzing the Moon's structure and history, scientists can develop models applicable to other moons in the solar system and to exoplanets around distant stars. Anomalies challenge assumptions, drive new hypotheses, and refine theoretical frameworks, showing that exceptions and irregularities are often the most informative elements in scientific inquiry. They reveal that celestial bodies, while appearing uniform from a distance, are shaped by complex interacting processes that unfold over billions of years. Appreciating the Moon's anomalies encourages a deeper respect for the intricacies of planetary evolution. Each irregularity, from the thick far-side crust to the placement of Maria and mascons, serves as a reminder that the Moon's formation was not a simple, uniform event, but a dynamic sequence influenced by impacts, orbital mechanics, and internal differentiation. By embracing these complexities, we gain a more nuanced understanding of how tidal forces, gravitational interactions, and planetary collisions combine to shape the features we observe today. The Moon's surface, with its asymmetries and anomalies, stands as a living record of these processes, inviting continual exploration and inspiring curiosity about the forces that sculpt worlds across the cosmos. In considering these alternative hypotheses and the evidence provided by anomalies, we also recognize the provisional nature of scientific knowledge. The Moon's formation story is not fixed. It is refined with each new mission, each new measurement, and each new model. Scientific understanding evolves as our tools improve and as theories are tested against data. By observing, analyzing, and questioning, researchers gradually assemble a coherent picture of lunar history, one that integrates giant impacts, orbital dynamics, crustal evolution, and tidal interactions. In this way, the Moon becomes both a subject of study and a teacher, illustrating the iterative, evidence-driven process by which humanity uncovers the secrets of the universe. As we bring our journey with the moon to a gentle close, it is worth reflecting on the intricate forces and processes that have shaped its familiar face. Tidal locking, the phenomenon by which the moon's rotational period matches its orbital period around Earth, is the central feature governing its steady orientation. This state was achieved over billions of years through the persistent action of gravitational interactions, tidal torques, and the dissipation of rotational energy within the moon's interior. The moon is not simply stationary. It is subtly flexing, adjusting, and responding to Earth's pull. A dynamic process rendered invisible to casual observation, but crucial to the cosmic stability we now perceive. Gravitational interactions have been the architects of this enduring arrangement. Earth's pull raises tidal bulges on the moon, and the moon's pull shapes tides on Earth, producing a continuous exchange of angular momentum that gradually synchronizes rotation with orbit. Observations from lunar laser ranging experiments conducted since 1969 confirm that the moon recedes from Earth at roughly 3.8 centimeters per year, an ongoing consequence of these energy exchanges. These interactions demonstrate that tidal locking is not a static outcome but a persistent negotiation between celestial bodies, a conversation conducted in forces and motion over incomprehensible spans of time. Librations add nuance to this picture, revealing that the moon is not a perfectly rigid body, but one with internal flexibility that allows for slight oscillations. Longitudinal, latitudinal, and diurnal librations combine to allow Earthbound observers to view approximately 59% of the lunar surface, extending our understanding of its geography and internal structure. Contributions from astronomers such as Eleanor Helin have refined our models of these oscillations, demonstrating how subtle gravitational effects interact with the moon's shape, internal composition, and orbital eccentricity to produce a slowly shifting, yet reliably familiar face. High-level theoretical perspectives have broadened our appreciation of the moon's behavior. Spin-orbit resonances, early chaotic rotation, and orbital instabilities reveal the complexity of celestial mechanics and underscore the delicate balance required for tidal locking to emerge. Jacques Lasker's work on long-term planetary evolution illustrates how even slight variations in mass, orbit, or eccentricity can influence rotational and orbital outcomes, while studies of moons such as Io, Europa, and Enceladus demonstrate the universality of these processes across the solar system. The early Earth-Moon system likely experienced periods of instability and high eccentricity, yet the persistent action of tidal forces and angular momentum transfer gradually produced the stable, synchronous rotation we observe today. The Moon's influence on Earth extends beyond physics into the realms of ecology, climate, and human culture. By stabilizing Earth's axial tilt, the Moon maintains moderate seasonal variation, creating a predictable environment that has supported the evolution of complex ecosystems. Tidal rhythms, influenced by the Moon's gravitational pull, have guided biological cycles, from the rise and fall of intertidal organisms to circadian and reproductive rhythms in terrestrial life. Astrobiology research, such as that conducted by Brian J.P. Copeland, highlights how these predictable cycles provide both opportunities for life to adapt and frameworks for long-term ecological stability. Even human societies have been shaped by lunar cycles, which informed early calendars, navigation, and cultural rituals connecting the motions of the Moon to daily life in subtle yet profound ways. Exploring lunar anomalies and alternative hypotheses further enriches our understanding. Variations in far-side crust thickness, the distribution of Marianne mascons, and gravitational irregularities challenge and refine our models of lunar formation. The giant impact hypothesis, proposed by William K. Hartmann and Eric Asfaug, remains the most widely accepted model, explaining many observed features, while alternative theories, such as the capture hypothesis, offer additional perspectives for consideration. These anomalies highlight the evolving nature of scientific knowledge, showing that observation, experimentation, and theory must continually interact to reveal the Moon's history. By appreciating these complexities, we recognize the Moon as a dynamic, multifaceted object, shaped by forces both visible and hidden. From a cosmic perspective, the Moon embodies the patience and persistence of physical laws. Its steady face, the familiar Maria, and the rugged far side are all products of billions of years of gravitational negotiation, rotational adjustment, and orbital evolution. While human lifetimes are fleeting, the Moon's rotation, orbit, and librations operate on a scale that encourages reflection, a reminder of the vast temporal and spatial dimensions of the universe. The precision of these interactions, the predictability of tidal forces, and the balance achieved between energy dissipation and angular momentum transfer offer a calming perspective on cosmic stability. In a universe often imagined as chaotic or violent, the Moon exemplifies harmony, order, and the subtle elegance of physical laws in action. Finally, as you look up at the night sky, the Moon's face presents a constant companion, a guide and a witness to the passage of time. Its steady presence invites contemplation of the forces that shaped it and the delicate balances that sustain it. The contributions of lesser-known scientists, from George Howard Darwin to Eleanor Helin, remind us that understanding arises from careful observation, creative modelling, and persistent curiosity. By considering the Moon's tidal locking, gravitational interactions, librations, and internal dynamics, we gain insight not only into a celestial body, but into the principles that govern planets, moons, and exoplanets across the universe. The Moon is both familiar and extraordinary, a testament to the elegance of the cosmos and the interconnectedness of matter, energy, and life. In observing the Moon tonight, allow yourself to appreciate its calm, unchanging face and the subtle motions that lie beneath. Consider the billions of years of cosmic choreography that brought it to this orientation, the silent forces that maintain its stability, and the intricate balance that shapes its interaction with Earth. The Moon is at once a scientific marvel, a source of inspiration, and a steadfast presence, offering a bridge between human curiosity and the vast, patient mechanisms of the universe. By reflecting on these forces and observing the Moon with thoughtful attention, we are reminded of the remarkable order and beauty inherent in the cosmos, and the enduring power of physics to sculpt and sustain worlds across space and time.